Hello everyone, my name is Joel Tikku and today I'll be walking you through my project on counter fuzzying, a clever and surprisingly simple way to slow down software fuzzers and protect the application from being exploited. Now before we dive into the live demo, I'll start with some background on fuzzying and the concept of counter fuzzying. Now this will jump into, we're going to be jumping into the step-by-step live demo where I'll show you how I modified the program. I used AFL++ to fuzz it and observe the impact. Now you'll get to see the actual fuzzer output, which interestingly enough is themed like a pizza shop interface, and witness how a few lines of code can grind the fast process down into a crawl. Now, this project sits at the intersection of software testing, security, and performance analysis. I came from a basic background in C programming with a foundational understanding of cybersecurity. So I took on this project to explore how programs can resist fuzzying, which is a popular automated bug finding technique. Now, by making small but strategic changes to the code, um, fuzzying has become a standard practice in security research, uncovering countless bugs in software ranging from web browsers to network servers. That success is exactly why the idea of a program fighting back against fuzzying intrigued me and became the basis for this project. Now, to start with the basics, fuzzying is an automated software testing technique. Fuzzer rapidly sends a large number of random or mutated inputs to a program and watches for any unusual behaviors like crashes, hangs, or unexpected outputs. It's a bit like a stress test for software. We're trying to break the program by pushing it with unexpected, malformed, or edge case inputs. The idea is that by sheer volume and variety of inputs, the fuzzer might trigger hidden bugs that developers didn't anticipate. In recent areas, fuzzing has been used by major companies and security teams. For example, Google's Project Zero and open source efforts like OSS Fuzz, which were used to find and fix vulnerabilities before attackers exploit them. Now, fuzzing is incredibly effective because it's fast and intelligent. Modern fuzzing tools like AFL, which is a short for American Fuzzy Lop, or its successor AFL++, can execute thousands of test cases per second, far faster than any human testing. They don't just throw random data blindly, they mutate inputs intelligently based on feedback. Now, specifically, tools like AFL++ can are coverage guided, meaning that they monitor which inputs explore new code path in the program. So when an input finds a new path, the fuzzer keeps that input as quote unquote interesting case um, and makes more mutations from it to explore further. So this way, fuzzers can explore deep and complex bugs that traditional testing or manual code reviews might miss. Now, over time, a fuzzer can accumulate a wide variety of test cases that covers many execution paths, including one leading to a potential vulnerability. But that blazing speed is also a vulnerability for the fuzzer itself. Fuzzers rely on being fast and thorough to be effective. So if we can make them slow down, even by a little, we drastically reduce how many paths they can explore and how many crashes they can find in a given time. So this idea of fighting back against fuzzying is called counter-fuzzying. You can think of it as anti-fuzzying technique instead of the fuzzer attacking the program's uh, weaknesses. The program exploits the fuzzer's need for speed. So instead of using firewalls or encryptions, we're essentially throwing sand into the fuzzer's gear by intentionally adding delays into the program's execution. So the goal is to frustrate automated testing. A counter-fuzzed program wastes an attacker's time. It might still function normally for real users, but if a fuzzer tries to bombard it with inputs, the program deliberately runs much slower, making the fuzzer process painfully inefficient. Now let's talk about the project goal, how I planned this concept. So I want to take a real program and make it hard to fuzz, then observe the effects in a controlled experiment. Now for this, I chose CJSON, which is an open source C library for parsing JSON, essentially which converts the JSON text into a C data structures. It's small, fast, and has a clean test harness that's easy to work with. CJSON is widely used in embedded systems and applications for configuration and data interchange, making it realistic target for fuzzying and thus an interesting candidate for counter fuzzying. So the goal is simple: add a counter fuzzying mechanism to CJSON and see how a fuzzer's performance change. Um, Now, with the tools and environments, so to perform this experiment, I set up a dedicated environment. I worked in a VirtualBox VM running Ubuntu Linux to keep my main system safe from any crashes or side effects of fuzzying. I installed Clang for compilation and AFL++ for fuzzying, along with the typical build tool like Make and GCC. AFL++ is a community maintained fork of AFL with many improvements, and it provided the instrumentation and fuzzing engine for our tests. My workflow was entirely terminal based, writing code in a text editor, compiling it via command line, and running the fuzzer in a terminal. I ran AFL++ on a single CPU core for this demonstration, which is the default mode. AFL++ can also parallelize our multiple cores, but one core was enough to illustrate our point here. Now, using a VM and a controlled environment ensures that if the fuzzer found a crush or a hang in the system, it wouldn't affect my host machine. So the first step was getting everything ready. I installed the necessary packages like Clang, GCC, Make, and AFL++ using Ubuntu's package manager. With the tools in place, I downloaded the CJSON library source code and extracted it. Now, once extracted, I verified I could compile the library and run its tests in a normal way, just to make sure that the code worked properly before making any modifications. Essentially, I set up a baseline, a working CJSON parser, a test harness in my environment. The 40fuzz bench repository came with a seed directory for the CJSON containing collection of small CJSON files that could be used in initial input for fuzzying. The seeds are examples of typical JSON snippets, which can help the fuzzer get started with valid input structure. Now with working baseline, I proceed to introduce the counter fuzzy mechanism. So I added a delay loop to the program that would only run when a certain condition is met, specifically when an environment variable is set to true. By using an environment variable, let's call it CJSON slow input, I could turn the slowdown on and off without recompiling the code. So in normal cases, the program runs at full speed. And in slow cases, when the variable is set to yes, the program executes a long time. This useless loop that simply burns the CPU cycle for a few seconds before continuing. With this modification in place, I could easily switch between the original fast behavior in the slow mode just by toggling the environment flag. Yeah, so that covers the basic idea and setup. Now it's time to see this in action. So I'll walk you through a live demonstration of how I implemented the counter fuzzing in CJSON and what effects it has on AFL++. We're going to go through setting up the project, modifying the code, compiling, and running the fuzzer, both before and after enabling the slowdown. Now to begin, I make sure we're starting fresh by deleting any old copies of the project repository. This makes sure that there are no leftover files that could conflict with our demonstration. So once I do that, then I clone the official repository provided by the professor. It contains multiple benchmark targets for fuzzying. Our focus will be on one of them, which is the CJSON, like I've mentioned before, which is a lightweight C library for parsing JSON. So the next, what I will do is I'll extract the CJSON archive. This gives us access to the source code of the library so we can build and test against it. So this puts inside the actual source directory where we'll create a custom taste hardness for fuzzying. Now the default tests in CJSON are well structured, but they're not designed for fuzzying. They don't take external inputs. That's why we're creating our own taste program here. It accepts a file as an input, reads it, and parse it with CJSON, and optionally adds a delay if a certain environment variable is set. This makes it fuzzable and allow us to experiment with performance manipulation. So let me just put the source code here. So this is the source code. So this code checks if the CJSON slow input variable is set. If so, it enters a loop that burns CPU time, simulating slow parsing. Then it reads a JSON string from a file, or uses a default one if none is given. Parse it and print the name field. Now we compile the test program normally using GCC. Let's run the compiled binary, which is the executable file produced when compiled our C code using GCC. I'm using the time command here to measure how long the program takes to run. So which here it shows under real how long it would take, or the total time it takes from start to finish, like using a stopwatch. Now we test it with a slowdown enabled by setting the variable to yes. And once we execute that, you will see a noticeable pause, which results showing that there's a difference, obviously, in milliseconds, which confirms the delay loop is functioning. This setup mimics performance-heavy scenarios like those exploited in denial of service attack or DOS attacks. We can now unset the variable to go back to the normal mode. Now to prepare our program for fuzzying, we recompile it using AFL++, special compiler, AFL Clang Fast, which adds coverage tracking instrumentation. So this binary is ready to be fuzzed now. So let's now prepare the input directory, which already exists with the sample JSON file. So this file will be used as the initial seed by AFL++. We'll now launch AFL++ in a fast mode without any delays. And we make sure that it suppress any warnings by setting the AFL I don't care that missing crash flag. Once it starts, you will see AFL++ dashboard, and the key matrix includes executives per second, which shows it's pretty fast. Path found usually stays low since we're not changing logic. And the coverage age, which is still useful for performance benchmarking. This confirms the fuzzer is working efficiently, running over thousands of tests per second. Now let's activate our slowdown mechanism to demonstrate counter fuzzying. Let's enable the flag, the CJSON, so input variable, and this time we use a T3000 flag to give AFL++ a longer timeout per input, which in this case it would be like 3 seconds. So without these, AFL++ would abort inputs that seems to hang. So now watching the difference now, the executions per second, it dramatically drops here, and the dry run time spikes. As you can see, you'll clearly see that the fuzzing throughput has plummeted. The program behaves the same way in terms of outputs, but the performance hits render fuzzing dramatically slower. This, in essence, is counter fuzzing, which we are sabotaging the performance without crushing the program. So let me go ahead and unstate the variable to return to the terminal, to the normal state. Well, so what we just saw essentially is a live demonstration of how counter fuzzying can be implemented using subtle delay mechanisms with a single environment variable and a loop. We slowed down the fuzzer by over 99%. So this doesn't block the fuzzer or produce invalid results. It simply makes the fuzzer inefficient. For security researchers or developers, this showcase how performance-based bugs can be tested. For adversaries, it's a tactic to evade deep fuzzying. So overall, we proved that by introducing a slow path in the code, we can directly measure AFL++ speed drop, making counter fuzzying both practical and observable. All right, so we've seen the live demo of counter fuzzying in action. Now I will summarize the results and talk about the broader picture, why this works and what it means. So, given the result summary, the demonstration obviously confirmed that our counter-fuzzying logic had the intended effect. With the environment flag off, the fuzzer ran at full speed, and it was unhindered. However, with the flag on, we saw an astronomical drop in speed. And it is important to note that we did not change what the program does with the input at all. The JSON was still parsed correctly and the output was the same. So all we did was add a time delay, but the delay was enough to drastically hurt the fuzzer's efficiency. And in a fuzzing campaign, time is everything. If you can only test a few dozen inputs in the time, You could have tested, thousands or millions. The odds of finding a rare crashing input becomes extremely low. So in summary, the counter-fuzzing measure worked exactly as I hoped it would, uh, and made the program much harder to fuzz in any reasonable time frame. In a real fuzzing scenario, such a slowdown means that an issue that might have been found in minutes could now take days or weeks to surface, if ever. The fuzzer's effectiveness is basically neutralized as long as the slowdown is inactive. Now, why this works? Why does such a simple change have a big impact, right? Because fuzzers like AFL++ are greedy and time sensitive. They thrive on being able to test thousands of inputs quickly. If an input takes too long to process, the fuzzer treats it as a hindrance. It might even abandon the input, uh, thinking the program got stuck, or significantly reduce how often it tests similar inputs. So by wasting the fuzzer's time on execution, we prevent it from doing what it is really good at. So essentially, fuzzers prioritize fast path. They will skip or penalize any test cases that seem slow or unresponsive, focusing instead on other path that yields quicker feedback. Now, counter-fuzzing trick exploits these spaces by making every input path slow. Uh, we give the fuzzer no fast alternative to pivot. Uh, it either has to slog through our delays or give up. That was the two options, right? So in our demo, we force it to slog, uh, and so we can see that how ineffective it became. So think of it like an assembly line that is optimized to take many products quickly. So if you force the line to move in a slow motion, it doesn't matter how good the inspectors are, they simply can't inspect as many products, right? Um, Now let's look at the implications of counterfuzzing. So the idea of counterfuzzing opens up some interesting discussions. On one hand, it can be seen as a defensive technique. Imagine you have a piece of critical software that you suspect attackers will try to fuzz vulnerabilities. If it's not easy or timely to update, perhaps if it is a legacy system, adding a counter-fuzzing delay could make it much harder for attackers to find bugs, giving you or buying you some time or deterring them altogether. So it's a bit of a stopgap security measure. It doesn't fix any vulnerabilities, but it makes them harder to discover. Now, on the other hand, this technique raises ethical and practical concerns. So, a developer could misuse it to hide poor data quality or code quality. So, for instance, any unscrupulous vendor might add delays to their software to pass a security audit, knowing that the auditor's fuzzing tool will hardly scratch the surface in a reasonable time. It could also frustrate legitimate testing efforts by quality assurance teams. So, in short, counter fuzzing is a double-edged sword. So, it can be a clever defensive layer um, when using sparingly and transparently, especially in scenarios where performance isn't critical. But can also be seen as anti-testing or security through obscurity if abused. It's important to consider the context and intent when applying such measures. So in our case, we're using it as a learning experiment, not deploying it in a production system. Additionally, if counterfuzzing becomes common, fuzzing tools might evolve to detect these tricks. And conversely, a program could check how often or how erratic inputs are received and only then enable the slowdown, in effect detecting, am I being fuzzed right now, right? And responding accordingly. Likewise, fuzzing tools might evolve to detect deliberate delays and attempt to work around them. So it's a bit of an arm race. Um, so what I learned, working on this project taught me a lot about fuzzing process and low-level software behavior. I gained a deeper understanding of um, how fuzzers like AFL++ uh, work. I got a hands-on experience with the compiler instrumentation. I learned about performance profiling and measure execution speeds in fuzzing context. I also improved my troubleshooting skills. Um, and looking at the challenges, the project was not without its challenge. A few notable hurdles I overcame is tools and compatibility issues. Initially, I tried compiling the program with GCC and using AFL++, but AFL++ expects to use its own instrumentation plugin with a certain compiler that wasn't compatible with the GCC version. Um, but overcoming these challenges made this successful demo even more satisfying and exciting. If you're interested in trying something like this yourself, here's a few tips. Start small. Use a simple program like our small JSON parse test as your fuzzing target when experimenting with Fuzzer or counter fuzzing for the first time. It's easier to understand what's happening, and you won't be overwhelmed by complex behavior. Um, the key takeaways I would say is that fuzzing is powerful, right? Automated fuzz testing can throw a huge number of inputs, programs that find bugs that would be almost impossible to discover manually. So it's a cornerstone of modern software security testing. And because of how thorough and fast it is, and many critical bugs in softwares have been found thanks to the fuzzer. But its weakness, that string speed can also be a weakness, right? So if something causes the fuzzing process to slow down, like the intentional delays we introduced, the fuzzer's effectiveness drops dramatically. It's like trying to sprint through mud, right? And so counter fuzzing is a real technique. So we just gave a few lines of code. We implemented a basic counter fuzzing technique, and it doesn't prevent uh, someone from analyzing or exploiting a program forever, but it definitely raises the bar. It's not a silver bullet. Counter fuzzing isn't a substitute for fixing bugs. It is more of a speed bump for attackers or testers. So for long-term security, you'd still want to use Fuzzer to find and fix issues, and counter fuzzing just buys you time or discourages optimistic attackers. So in essence, we demonstrated an arm race dynamic. As testing tools get smarter and faster, developers can add tricks to slow them down. So it's a fascinating back and forth in the realms of software security. Thank you so much for listening, and I hope this project gives you an insight to how fathers work and how software can defend itself in such unconventional way. So this project was a great way to bend my interest in security and performance tuning, and it demonstrates that sometimes a simple change can have a big impact. Um, Thank you.